Today we are going to discuss the problems on distribution functions and Bayes' theorem. First, we give the definition of marginal cumulative distribution function. Marginal cumulative distribution function of joint cumulative distribution function capital F of x comma y is defined as limit y tends to infinity capital F of x comma y dy, and marginal distribution function of fy comma y is defined as limit x tends to infinity f of x comma y dx. If we want to find the marginal cumulative distribution function of x, means you have to differentiate f of x comma y with respect to y. If you want to find the marginal cumulative distribution function of y, means you have to find the limit of f of x comma y with respect to dx. Next definition, marginal probability density function of x and y. Let x and y are the continuous random variables and small f of x comma y be the joint probability density function. Then the marginal probability density function of x is defined as fx of x is equal to integral f of x comma y dy for all x. Here to find the marginal probability density function of x, you have to integrate f of x comma y with respect to y. And in a similar way, we can define the marginal probability density function of y as fi of y equal to integral f of x comma y dx for all y. Next, we give the definition of conditional distribution of x on given y equal to y is defined as f x given y of x comma y equal to f of x comma y divided by fy of y, where small f of x comma y is the joint density function of x and Fi of y is the marginal density function of y. So here Fi of y not equal to 0. Next, we give the definition for conditional distribution. The conditional distribution of y given x equal to x defined as f y given x of y given x is equal to f of x comma y divided by fx of x, where f of x comma y is the joint density function of x and y and the fx of x is the marginal density function of x, where fx of x not equal to 0. Next, we give the problem. Let x and y are the jointly continuous random variable with the joint probability density function fxy of x comma y equal to c into 2x plus y when x takes the values between 0 to 2 and y takes the value between 0 to 3. Now, f of x comma y will be equal to 0 elsewhere. Now we have to find the constant value c. Now it is given that f of x comma y x is a joint probability density function. Therefore, its double integral value will be equivalent to 1. Double integral f of x comma y dx dy equal to 1. Now substitute the value of f of x comma y as c into 2x plus y dx dy, where x takes the value between 0 to 2. So lower limit of x is 0, upper limit of x is 2. Similarly, the lower limit of y is 0, lower limit of y is 3. Now take c outside and you will integrate with respect to x facts first. So now you get on integrating, you take 2 as it is. While you are integrating x with respect to x, we will get x square by 2. You keep y as it is. While you are integrating dx, you will get x. Now substituting the value, upper limit minus lower limit. X value, wherever x comes, you replace it by 2 minus lower value. So now x இருக்கிறது 2 போடணும், x square by 2, 2 square by 2, 4, and then divided by 2 plus y into x value is 2. Lower limit value is 0, so therefore we omit it. So now cancelling 2, 2, you will get 4 plus 2y into dy equal to 1. Next you integrate with respect to y. 4 into dy, while you are integrating dy, you will get y. You keep the 2 as it is. When y dy is integrated, you will get y square by 2. Then apply the upper limit minus lower limit. Upper limit value of y is 3. So 4 into 3, 12, plus 2 into 3 square, 9 by 2. 2 to get cancelled. Now y equal to 3, you will get 3 square. So 3 square is 9. Now final answer is 12 plus 9, 21. 21 c equal to 1 and c equal to 1 by 21. Next, we see the problem on marginal density function. The joint probability density function is f of x comma y equal to a into e power minus 2x plus y, where x greater than or equal to 0, y greater than or equal to 0. Now we have to find the value of a marginal density function of x and y. So now, in a similar manner, we can find the now we are given that f of x comma y is a joint probability density function. Therefore, double integral value f of x comma y dx dy equal to 1. Now replace f of x comma y by a into e power minus of 2x plus y dx dy. Here x takes the value between 0 to infinity, and y also takes the value between 0 to infinity. Now you take a outside, integral y equal to 0 to infinity, x equal to 0 to infinity. You take e power minus 2x plus y as separate e power minus 2x into e power minus y dy. First you integrate with respect to y. Now, splitting the integral into two parts, y equal to 0 to infinity e power minus y dy, and x equal to 0 to infinity e power minus 2x dx. On integrating e power minus 2x, you will get, with respect to x, you will get e power minus 2x divided by minus 2. And substituting the value, upper limit minus lower limit, e power minus infinity. 2 minus 2 into infinity, you will get e power minus infinity minus e power 2 into 0. Anything power 0 is 1 and e power minus infinity is 0. So therefore you will get the final answer as 1 by 2. And you take 1 by 2 outside, you will get a by 2 integral e power minus y dy equal to 1. Now integrating e power minus y with respect to y, you will get e power minus y divided by, here we are minus 1. The minus 1 is obtained by differentiating minus y with respect to y. When y is differentiated with respect to y, you will get 1. So that 1 is written here in the denominator. And then you apply the upper limit as usual. You will get e power minus infinity minus e power 0. E power 0 is 1. Final answer on cancelling, you will get a equal to 2. And then marginal density problem. Next we find the marginal density function of x. you integrate f of x comma y with respect to y. Now replace the value of a is 2, so therefore you write 2 into e power minus of 2x plus y dy. While we are integrating with respect to y, you keep x as it is. So therefore the term e power minus 2x is taken outside, 2 is also taken outside. You have to integrate e power minus y with respect to y. The similar way, the value of your final answer will be equal to what? Now 2 into e power minus 2x is the marginal density function of x. In a similar way, we can find the marginal density function of y. It is obtained by integrating 2 into e power minus 2x plus y dx with respect to x. While we are integrating e power minus 2x plus y with respect to x, you keep y term as it is. So therefore e power minus y we take outside, and we have to integrate e power minus 2x with respect to x. While you are integrating e power minus 2x, you will get e power minus 2x divided by minus 2. Applying the limits e power minus infinity minus e power 0, you will get final answer will be e power minus y. Next we see the problem on theorem on Bayes theorem for two events. Now let A and B are the any two events, then the probability of A given B equal to probability of B given A into probability of A divided by probability of B. So this is the formula for Bayes theorem for two events. So now we give the proof for the two events. From the definition, we apply the conditional probability definition of A. The conditional probability of event A when the event B has already occurred is the probability of A given B equal to probability of A intersection B divided by probability of B. Similarly, the conditional probability of event B when the event A has occurred is given by probability of B given A equal to probability of A intersection B divided by probability of A. Name this equation as 2. Now from the above two equations we can find the value of probability of A intersection B from probability of A intersection B equal to probability of B given A into probability of A from the equation 2. Name this equation as 3. Substitute the value of the probability of A intersection B value obtained from equation 3 in 1. You will get probability of A given B equal to replace probability of B given A into probability of A divided by probability of B. Next we see the problem on Bayes theorem. It is a case study problem considering a set of patients coming for the treatment in a certain clinic. Let A denote the event that a patient has liver disease and B denote the event that he is an alcoholic. It is known experience that 10% of the patients entering the clinic have liver disease and 5% of the patients are alcoholic. Also, among those patients diagnosed with liver disease, 7% are alcoholic. Given that a patient is alcoholic, what is the probability that he will have liver disease? So now we first, we let A denote the event that the patient has liver disease, and let B denote the event that the patient is an alcoholic. We are given that the probability of a patient having liver disease P of A equal to 10% and it is equivalent to 0.1. Similarly, the probability of a patient to be alcoholic is probability of B equal to 5%, that is equal to 0.05. Also, the probability of a patient to be alcoholic when he already diagnosed with liver disease, that is probability of B given A equal to 7%, 0.07. And similarly, we have to find the probability that the patient will have liver disease when he is alcoholic. That is, you have to find the value of probability of A given B. Now we apply the Bayes theorem for the two events. Probability of A given B equal to probability of B given A probability of B given A into probability of A divided by probability of B. So this formula we have to apply. The probability of B given A equal to 0.07 into the probability of A 0.1 divided by probability of B 0.05. So on simplifying, you will get that result as 0.14. Next we discuss the case study problem, and it is for three events. The three factories A, B and C of an electric bulb manufacturing company produce respectively 35%, 35% and 30% of the total output. Approximately 1.5%, 1% and 2% of the bulbs produced by these factories are known to be defective. If a randomly selected bulb manufactured by the company was found to be defective, what is the probability that the bulb was manufactured by the factory A? So now let A be the event that the manufacturing a bulb from factory A, B be the event that the manufacturing a bulb from factory B, C be the event that manufacturing a bulb from factory C, and let D be the event that a bulb is defective. So we are given that the probability of manufacturing a bulb from factory A is probability of A equal to 35%, that is equal to 0.35. The probability of manufacturing a bulb from factory B is probability of B equal to 35%, which is equal to 0.35. The probability of manufacturing a bulb from factory C is probability of C equal to 30%, 0.30. The probability of a bulb to be defective when it was manufactured from the factory A is probability of D given A equal to 1.5%, 0.015. Similarly, the probability of a bulb to be defective when it was manufactured from the factory B is probability of D given B equal to 1%, that is equal to 0.01. Similarly, the probability of a bulb to be defective when it was manufactured from the factory C is probability of D given C equal to 2%, 0.02. We have to find the probability of a bulb to be manufactured by the factory A when it was found defective. That is, probability of A given D you have to find out. So here we are applying the Bayes theorem for three events. Probability of A given D equal to probability of D given A into probability of A divided by probability of D given A into probability of A plus probability of D given B into probability of B, probability of D given C into probability of C. So substituting the values and simplifying, you will get 0.356 will be the answer. Students, I hope that you understand the Bayes theorem concepts and marginal distribution concepts very well. I hope that. Thank you.